Data streaming is very powerful, but also very confusing to understand what can we build and what are the techniques we can use to build systems with data streaming. I have fully switched my career towards data streaming around 6 months ago. Since then, I've been trying to make sense of it, and I'm also still confused. So even with a lot of time dedicated to this, I still feel like we can make things a bit more understandable. So let's try to cover that. And then, of course, it's an ever-evolving thing. Would love to hear your feedback. But let's start with what would be the big building blocks around data streaming. As we look into this pyramid and the layering around data streaming, so of course we have the data streaming bus. The data streaming bus will allow us to do the data streaming, but it has different capabilities like durability, and you can also nowadays with some techniques with, let's say, Confluent Tableflow or syncs towards Iceberg or stream-based, you can also have directly query in forms of SQL or key value from the data bus. This is going to provide async processing, general pub/sub with multiple consumers in isolation, acknowledgements of individual messages, and durability accordingly to your taste. Could be seconds, days, or even infinite retention. On top of this, we're going to have the layer of the stream processing. Stream processing will allow you to basically take data in or out from the data bus. The most known ones we see is the connectors side. So there is like Kafka connectors, there is bentos, there is multiple others, allowing you to connect dozens of storage types on all sorts of protocols from database, from RPCs, HTTP, and also proprietary protocols. So that's kind of the magic inside data streaming, is that you can connect from any system to any system. And of course, depending on the capability of those systems, you can achieve 100% data guarantee because the data bus allows for that. So this is where most of the revolution on data streaming comes from. Connecting point A to B with guarantees, observability, traceability, and low latency. What can we do with those things, right? So what we've been seeing in the industry is that there is more specialization now. Before, we would only be talking about Kafka and stream processing, the forms of consumers and producers, or maybe specialized frameworks like Kafka Streams, and then Flink. But there is way more to this. It may feel today that data streaming is becoming more fragmented, and it's true. Because if we also look on top of the stream processing, we'll see two big categories who are becoming more notable and actually with very successful use cases and businesses built on top of it. So one is the durable execution frameworks. Here we are talking a lot around orchestration of data. So you can do SAGAs, you can orchestrate different services, and you can do that with durability, which is extremely important, of course, but also the same guarantees. So then this is a very common problem we find in pretty much any backend system in any enterprise at any scale. The other one is incremental view maintenance. As you are, it's very common to see use cases where you're going to take data from your source of truth and move it to an analytical store, to a data warehouse, or to a search index, to a cache, storage, object stores, and etc. So it's very common that you use streaming to maintain a view, a specialized and denormalized view for that data you have. This way, we are doing sort of a CQRS at architectural level, where you can still do your writes and your commands on the source of truth, but now you're reading data from a more specialized place in a more specialized storage, or pushing this forward. So this incremental view maintenance, this is part of the incremental processing side of things, and allows you to reshape your data, but then keep it up to date in real time. It's an analogy of what we would do with views inside of the database, but with real-time updates, and it's actually a copy, which means you're not talking directly to the source of truth data anymore. In the middle layer, which I skipped here, but what we can do is streaming ETL, aggregations, temporal joins, enrichments, and many use cases that you can derive from this. For those categories, this is what we're going to call the complex event processing, which then allows you to basically achieve many primitives of communication and data manipulation inside of a system. With those techniques, you can pretty much cover anything, especially if they are asynchronous, but many use cases which are synchronous can also be asynchronous, but of course, you can also blend the two things together. Synchronous calls with events on the side, but you can also have batches for doing bulk of processing and then catching up on real-time data. There are many things here to be explored. On the left side, we have the governance layer. So here we can be talking all the way from PII data filtering, from doing policy management in real time, access, RBAC, and etc. And then you have UI and management layers. So in the ecosystem, we are going to have many options. There is like UIs to explore data inside Kafka, UIs to explore Flink or Kafka Streams management or Kafka Connect, or to do the whole telemetry and observability across the whole stack. So there is also like a huge market on that side. When we look into what those building blocks can give to us, there is just so many use cases, but I tried to put here what would be the techniques in which we can use. These techniques could go from orchestrating services and microservices, autonomous microservices, CAP architecture, Lambda, event sourcing, event-driven architectures, data mesh, governance, dynamic workflows, durable and temporal workflows. So like even when we talk about, for instance, AI agent, it's a durable workflow with microservices orchestration. The durability here is important because now we're talking about agents who can never die, let's say. Asynchronous distributed transactions, SAGAs is a great example. Real-time monitoring, not from the sense of just telemetry, but actually doing critical path changes, so from fraud detection to blocking IPs in a web application firewall. Anything on the real-time monitoring is possible with data streaming. IoT processing and temporal digital twins, these are also very big use cases we see here. So these are more like the primitives of what you can build in terms of use cases. So if we were to break this down here, we would have hundreds and hundreds of possible use cases. So the way to think about this is more like, what kind of capabilities are we getting on the plumbing and the building blocks across data streaming, and what can we build with those primitives? Once you have data guarantees and workflows and orchestration and the ability to play back to isolate consumers, it's multiple layers, right? You're doing the durability with PubSub, with delivery guarantees, with low latency. So then you are basically, part of the challenge here is like, how can you mix and match all of those techniques to create something which makes your software and your use cases easier to develop, yet robust, production ready, scale ready. Let's dive a little bit further into the data streaming processing framework, because there is a lot we need to cover here. How does the general picture looks like, right? So let's start with what comes from the data bus. So we need to understand delivery guarantees. So we are talking about at most once, which has data loss, at least once, which means that you're going to see the same message more than once, but still with ordering guarantees, or exactly once, which then you're guaranteed to do that only once. That's a bit more rare and doesn't work for all the connection sides, but certainly a possible processing methodology as well. On the connector side, again, this is one of the biggest parts of data streaming. So we can have two sides. One is the source, which is extracting the data from multiple sources. So then you can have two dimensions. You can have bounded data. So let's think of CSVs or files or data which is limited in size, could be a table, could be a query within the table, to unbounded, which would be stream processing. So that could be another stream source. That could be just IoT, telemetry, could be webhooks handling. There is just unbounded. You're always receiving new information. Could be data changes and etc. When we talk about, so Kafka is here, APIs. So like you can talk directly to, any protocol again. On the database side, we would have two ways. So the traditional polling. So you can have like a streaming to do sources of like SQL and pull the data for you. But of course, the most utilized way is the change data capture. Change data capture will do the transaction logs scraping, just like a database replica would do, and then produce events out of that. So then you have now a real-time stream consumption of your database. This is utilized for many use cases, from producing messages without dual writes and delivery guarantees, but also to do strangling fig pattern and move legacy systems and help with data integration on high-scale legacy systems, for instance. On the sync side, which is the load and delivering to other places, of course, any protocol is available again, so from object stores to proprietary databases, APIs, and etc. You can go as far as go through WebSockets with technologies like Lightstreamer. You can go to databases of any sorts and kinds. So then, again, the streaming ETL technique allows you to do materializations, to move data between points A to B with guarantees and consistency. So that's a big deal. You can warm up caches. You can warm up your search caches, your analytical engines. You can feed all the microservices. You can do event sourcing and etc. So this would be, let's say, the key points. But then once you're processing data, you also have to understand what is the execution context of the streaming. So it can happen in two ways. You can have isolated, so you have like stateless execution. And these you can do with single records or multiple records. Single record means every time a message passes by, you can only see it. You cannot see the message before, you cannot see the message after. And in this case, where you have no state, it means you can only use the information you have in hand or query from outside Word, like an API call or another storage, and bring extra information. So that's not like it doesn't allow you to look inside a window. Once we go to stateful computation, we can also do both the multiple record, but also single records. But now you're allowed to look at data within a window context. You can also look from previous windows in case you have saved that in the memory context. So now you're talking about like comparing events across time, to do real-time aggregations, to do, for instance, metrics in which you want to check the difference between a previous number and a new number. So let's say if you have a score which you apply with AI based on a 5 minutes window, and then you say the score and the probability of this is 0.9. On the next batch, the next step, it has dropped to 0.8. You can generate an event out of that. So you can analyze the stream as it's happening with window guarantees, and then you have multiple window types. You're going to have from time-based windows. So this could be tumbling windows, which are rolling. It could be fixed time windows, so like every 5 minutes, but without the messages from the last 5 minutes. So each of these are going to give you different guarantees and different meaning to the data for different use cases. You can do stream joins as well and stream to static data joins. This will allow you to look at, I don't know, let's say if you're doing fraud detection, you're going to look into multiple streams of data, but you're also going to eventually take data from another source of truth store, like a credit score system. So you are able to join all of those things and make decisions in real time. So with this, we cover, let's say, the primitives of that. Something which is also part of this, let's say, the main flow would be transformation. You're going to have frameworks that allow you to do transformations with user-defined functions, like most of the technology in stream processing are going to be Python or Java. Java is the key one. In Python, you have some implementations as well, but then with user-defined functions, and some vendors implement WebAssembly, some implement native C compilers, and etc. So you may have here a variety of languages you can do user-defined functions. Some also do that declaratively or SQL-based, YML, etc. So there are many options here in how you can transform the data. So moving fields between point and AB, splitting messages, one message into many messages, taking data from external sources and then chunking to the message, doing the materialization as well. So I collect messages one after the other, and then I produce a new enriched message. You can do it with like external protocols, APIs, databases, or the in-context memory you have, depending on the stream processor engine you have. Now we go to the specialization frameworks, but before we go there is like a set of primitives that you need for complex event processing. So because the data is in movement all the time and you want to have the delivery guarantee, so like data streaming would not have any of its value that we have today if we didn't have delivery guarantees and execution guarantees. So like the beautiful thing is like, can I get 100% of my data between point A to B? To do that and to be resilient to failures, to be resilient to either the infrastructure, software failure, faulty messages, and basically, can I upgrade my software and change the semantics while I still have that state? There's a lot of work that goes into this. So you're going to see complex event processing framework supporting watermarking to know exactly where stream processing has stopped. Allows you also to know how much you want to rewind in case of failures. So there is a bunch of trade-offs related to this. You may have transaction support, checkpointing for, let's say, major version upgrades or change of logic upgrades, out-of-order event handling, and dead letter and errors handling, which is also a big topic, especially if you depend on ordering controls. So complex event processing is part of what enables, let's say, use cases like IVM or durable execution, but also if you want to have stateful aggregations and trust in the point A to B side. When you look at Kafka Connect, for instance, like it doesn't support any of those things. It's really meant for moving data between point A to B, and failures can be sent to a dead letter, but that's going to be a simplistic implementation, which may break the semantics of your topic. So it really depends on the use case, how you want to implement these techniques. Durable execution, again, great for orchestrating services, orchestrating even within the same services, you need to orchestrate multiple steps. So as you need guarantees of doing Usually we're going to be talking about tens, if not hundreds of steps towards achieving one outcome in a series of steps within a backend system. Durable execution is amazing. There are also new initiatives like restate.dev, but we see that temporal.io is one of the big players here for sure. If you look at NA10 for AI use cases, same semantics. So think of workflows, DAGs, and anything that allows you to orchestrate through multiple steps. Now, the beautiful thing about having a lower level framework here is that you can also do dynamic workflows. So you have the full possibility of changing the path of your DAG or the path of your workflow based on new input. I'm going to use the AI agent example here as well. But of course, as the AI is also discovering the next steps of execution, you still want to guarantee that those steps are going to be concluded, right? So there is a ever-growing to-do list an AI agent is going to have. So this kind of lower level frameworks allows you to build that instead of building from scratch. Incremental view maintenance, again, it's an excellent technique for you to do, of course, data engineering, but you can also just digest and prepare data for your backend use cases. So think of taking a source of truth data, denormalizing it, and accumulating points to, let's say you want to keep the counts of gamification from a certain player. You can totally do that with incremental view maintenance and never have a query that does that periodically or cron jobs. You can just do it as you go. You can also generate more specialized data merging, which is also very common before you prepare data for caching or for search or analytics use cases. There's a lot more you can do with this. This can also be utilized, for instance, between autonomous microservices. So consider a use case where you have two microservices and one of them depends on the data from the other. Instead of creating a synchronous connection or having a full copy of the data from one microservice to another, you may want to have a specialized copy of the data. You can basically create a table inside of that other microservice with the necessary data they have. So they can operate autonomously without ever having to make network calls or wait for the data from another service. A bunch of semantics here makes it rather complicated. For instance, the watermarking, and then how much delay do you accept between the data? How do you cascade into tens, if not hundreds of... This pretty much paints the whole stream processing capability. What are you missing here? I think those components are very, very powerful to create a bunch of different systems, but at the same time, not always you'll find things with the same languages or with the same primitives. So tell me your thoughts. What is missing from this list? And then I'm also very curious, which use cases are you thinking of building with such techniques? And see you next time.